Routing for low power and lossy network RPL, routing protocol for the Internet of Things, IoT, and its security challenge. My name is Faisal Ali Garba, and I am a PhD student at Computer Science Department, Ahmadu, Bello University, Zaria. My research bio. My name is Faisal Ali Garba, and I'm a PhD student working on resolving packet dropping attacks, routing for low power and lossy network RPL protocol, the Internet of Things, Internet Protocol IP version 6, low power wireless personal area network. And packet dropping attacks are distributed denial of service attacks, where malicious devices drop missed packet by exploiting the vulnerabilities inherent in the standard RPL protocol, RFC 6550 of the 6LoWPAN network. My research involved accurate resolution of the packet dropping attacks in RPL, Blackhole, Sinkhole, Selective Forwarding Attack, and on-off attack using trust scheme in combination with Distributed Intrusion Detection System and a two-hop Acknowledgement Packet scheme. I developed an efficient hybrid encryption scheme for securing short message service during my MSc dissertation that consists of using Elliptic Curve Diffie Hellman to exchange Blowfish Encryption algorithm key in the presence of in the middle attacker. My research interests include network security in wireless sensor network, IoT, mobile Adhoc Network, vehicle Adhoc Network, flying Adhoc Network, ethical hacking, malware, reverse engineering, and antivirus evasion. And I am very active on Researchgate. This is the outline of the presentation. Routing in the Internet of Things IoT devices. Internet of Things IoT devices is a network of physical objects called things that are equipped with sensors, software, and other technologies in order to connect to the internet and exchange data with other devices and systems. This is a definition according to Oracle 2021. Now, billions or even trillions of these devices can be connected to the internet using IP version 6. And these devices in the IoT forms a network of constrained devices referred to as 6LoWPAN. We have seen what the abbreviation of this 6LoWPAN means. And in figure 1, we can see the IoT system model, where we have IoT devices that form this 6LoWPAN network, where we have devices with pressure sensor, with temperature sensor, with humidity sensor, with motion sensor. These are IoT devices that with these sensors. And then they are connected together, and then they are also connected with the border router. Now the border router is the same thing as the root node, also called the sync node. Now the border router acts like a mediator between the 6LoWPAN network and then the external TCP IP network. That is the external, that is the internet, basically the internet. So the pressure, the data obtained from the pressure sensor, from the temperature sensor, from the humidity sensor, from the motion sensor, all of them they collect their data, and then they'll transfer it to the border router. Now the border router will transfer the data to the cloud server. Now so that the user of this Internet of Things network will be able to access that data via the mobile application, as we can see it in this system model. Now the three-layer architecture system, if you go to, is the most basic IoT architecture in use. So we have this IoT three-layer architecture where we have the application layer, the network layer, and the perception layer. Now we are concerned with this presentation, we are concerned with the network layer, that is the middle layer. Now the routing layer and the encapsulation layer form the network layer, as we can see it in figure 2. So this network layer consists of the routing layer and the encapsulation layer. The routing layer, which is the one we are concerned with in this presentation, manage packet transfer from source to destination, and the packet is generated by the encapsulation layer. Now, routing for low power and lossy network RPL, cognitive RPL, COP, channel aware routing protocol CAP are some of the protocols used at this routing layer. And the protocols used in the encapsulation layer include the 6LoWPAN, the IP version 6 over time slotted channel hopping, the IP version 6 over network of resource constrained nodes, 6LoW, and IP version 6 over G.9959, and IP version 6 over Bluetooth Low Energy. Now, 6LoWPAN is the major protocol for communication over IoT networks, and 6LoWPAN acts as a link between low power devices and the IP wall, as we have seen it previously. Now, this 6LoWPAN combines IEEE 802.15.4, which is low rate, low data rate wireless personal area network, also called, that is the 802.15.4, is also called low data rate wireless personal area network. It is a standard. And then we have the IP version 6 protocols. Now, it uses the compressed IP version 6 protocol for networking and IEEE 802.15.4 as a data link and physical layer protocol. Now, this integration provides for a full interoperability with the internet. Now, in Figure 3, we can see the 6LoWPAN protocol stack. Now, let's go to Figure 3. This is this Figure 3 where we have the 6LoWPAN protocol stack mapped with the traditional TCP/IP protocol stack. We have the application layer and the 6LoWPAN network, and some of the protocols used is the COAP. While in the application layer, we have the HTTP protocol being used, and at the transport layer. In the 6LoWPAN network, it uses the UDP. While in the transport layer of the TCP/IP protocol, it uses TCP, both TCP and UDP. And then in the network layer of the 6LoWPAN network, it uses protocols such as IP version 6, ICMP version 6, Internet Control Message Protocol version 6, and the RPL, which is the routing protocol. And then we have in the network layer of the TCP/IP protocol stack, we have IP version 6, ICMP version 6, OSPF, etc. And then in the adaptation layer of the 6LoWPAN protocol, we have the 6LoWPAN. That is network layer and the adaptation layer map with the network layer of the TCP/IP protocol stack. And then in the link layer of the 6LoWPAN protocol stack, we have 802.15.4 MAC. While in the link layer, there are a variety of protocols that are being used. Also in the physical layer of the 6LoWPAN network, we have 802.15.4. Physical layer, while in the TCP/IP protocol stack we have variety of protocols that are being used at that particular layer. So a routing protocol is required to forward packet from one node to another in an efficient way. So all about routing protocol is about efficiency. How do you move packets from one node to another in an efficient way? Now that is where a routing protocol comes in handy. Now RPL is the only actual standard routing protocol in IoT networks. And RPL is a proactive distant vector source routing protocol. Now, a distant vector routing protocol in data network decide on the best route for data packet based on distance. That is why it is called a distant vector routing protocol. And a distance is a measure of the cost. When we say a distance, we mean a measure of the cost to reach a certain node. What is the cost of reaching taking a packet from one node to another? Now that is what relates to this concept of distance. Then source routing allows a sender of a packet to partially or completely spell out the route the packet takes through the network. RPL is a plan for collection-based network, as we have seen it earlier, as well as point-to-point to multi-point traffic. So collection, what we mean by collection-based network, we mean the data has been collected from all the IoT devices, from the data that's generated from the sensors that these devices contains. Now it will be transferred to the border router. Now from the border router to the cloud, from the cloud to the user's mobile device, as we have seen it in that IoT system model. That is why it's called collection-based network, as well as point-to-multipoint traffic. Now there might be a situation where the border router will now communicate, also send data to this individual IoT devices in the 6LoWPAN network. So it can either be from multi-point to point or point-to-multipoint traffic. Point-to-point traffic is also supported in the RPL. And RPL is based on the topological concept of directed acyclic graph, which is called DAG. Now, a DAG spells out a tree-like structure that defines the default route between nodes in the low-power Lossy network. Now, a DAG is a directed graph where all the edges and vertices are oriented in such a way that no cycle loops are supposed to exist. A destination-oriented DAG, or we call it a DODAG, is a DAG routed at a single destination, that is at a single DAG route, not at ongoing edges. The route of the DAG is usually a popular destination node, sink, or those providing a deeper route to the internet, that is the gateway. A single root node and multiple sensor nodes support each DODAG, as we have seen it in the IoT system model. So we have the root node has the lowest rank of 1, and the root node represents a collection point in the network. And the sink node, what is the root, is generally the link border router, the gateway, which joins the low power Lossy network to IP version 6 network. As we can also see it here. Here we have the border router having the lowest rank of 0, usually rank 0 or rank 1. And then now the rank will continue increasing as we go downstream further into the network. So this is just a sample of how an RPL network topology looks like. Now the root node handles the formation of a DODAG. The root node constructs a new DODAG that follows downward to the leaf node. I will come to see what a leaf node is. Now a DODAG is identified by 4 major parameters: DODAG ID, DODAG version number, RPL instance ID, and a rank. DODAG ID is an identifier that is distinguished by the IP version 6 address of the root node. An RPL instance ID is an identifier for an RPL instance. RPL instance is a network which may comprises of one or more multiple DODAGs. So when we say RPL instance, we mean a RPL network that may comprises of 1 or 2 DODAGs. Like in this figure 5, we have a RPL instance 1 that comprises of 2 DODAGs, DAG 1 and DAG 2. And we have RPL instance 2 with only 1 DAG, which is DAG 3. Now, a network may execute more than one RPL instance, but those instances are logically independent, as we can see it in figure 5. A node may connect to more than one RPL instance, but must only belong to one DODAG within each instance, as seen in figure 5. So as you can see, node 3 in DAG 2 also belong to DAG 3 in RPL instance 2. But a DAG 3 cannot belong to DAG 1. The node 3 in DAG 2 cannot belong to DAG 1 because it is the same RPL instance. The nodes are joined to one another in a tree-like manner within each DODAG in accordance with their ranks. And the rank of each node is a representation of its relative position to the root node in the DODAG tree. And the rank is an integer that portrays the location of a node within the DODAG. The rank increases downstream direction of the DAG and decreases in the upstream direction. So as we go down into the network, as I have said earlier, the rank will keep increasing. And then as we move up from the IoT node to the root node to the border router, then the rank will decreases. Loop avoidance and detection is not possible with the use of rank in RPL. Node also uses the rank property to separate between their parent and siblings in a DODAG. Now, a sibling of a node is any neighborhood node that shares the same rank with the node within the same DAG. Siblings do not necessarily share the same parent, and the part between siblings is usually not part of the DAG. A child node is a node with higher rank which joins to another neighborhood node known as parent node, which has a lower rank. Nodes that are not parent to any node are not as leaf nodes. And all upward routing to the root node is managed by having each node on the route transmit traffic through what we call a prepared parent. Now, all nodes in a DODAG with the exception of leaf node can be referred to as routers. A router here refers to a device that can forward and generate packet. A router cannot generate a new DODAG, but can only connect to an already formed DODAG. A host in RPL will refer to a node that do not forward packet, but can generate packet. So a host is the same thing as a leaf node, because a leaf node and a host, they are synonymous. They don't forward packet, but they do generate packet. Every node in a DODAG can establish a parent on a route toward the root in the formation process of the network topology and associate itself to a prepared parent, which is elected based on an objective function, OF. The rank is determined based on a specified objective function for each RPL instance. Now, OF, objective function, is a yardstick employed by RPL to construct the best path toward the root. The objective function specifies how RPL node convert one or more metrics into ranks and how to select and optimize route in a DODAG. Delay, link quality, connectivity are some of the routing metrics deployed by objective function for rank computation. Now, Internet Engineering Task Force, low power routing for low power Lossy network working group has standardized two objective functions for RPL protocol. Objective function 0, RFC 6552, and the minimum rank with hysteresis objective function MRHOF RFC 6719. Now, objective function 0 uses the minimum hop count metric to elect the best parent and route, while MRHOF uses the ATX metric. Global and local repair mechanisms are employed by RPL if there is a routing topology failure, link failure, or a node failure. Now, when a parent or a link failure occurs, a local repair mechanism tries to select a new parent or path. If more local failures occur, RPL performs a complementary global repair when the whole DODAG is reconstructed. Now, also the concept called trickle timer, which is employed by the RPL to treat inconsistencies occurring in the DODAG. The trickle timer interval is large when the RPL network is suitable. Route to loops, a new node joining a DODAG, a node moving within the network, and changing its rank are all events that are regarded as inconsistencies in the RPL. RPL messages are specified as a new type of Internet Control Message Protocol, IP version 6, ICMP version 6 control message whose structure is shown in the figure 5. So this is a sample of how a control packet within the RPL is being structured in the format of ICMP version 6. Now the this message, now I also call a this stands for DODAG Information Citation. One of the control packet used in the RPL is mapped to OX00 and is used to solicit a DODAG information object, DIO, from an RPL node. The this may be used to explore neighbor node in adjacent DODAGs. The this packet is multicast by a new node as a request to join the DODAG. So when a new node wants to join a DODAG, it transmit out a this packet, which is a form of a request that I want to join this DODAG. Now the DIO packet, that is DODAG information object packet, multicast through DODAG structure by the root to build a new DAG is mapped to OX01. Now the DO, that is DODAG information object packet, holds the necessary network information that will enable a node to find RPL instance, learn its configuration parameters, elect a DODAG parent set, and maintain the DODAG. DO is periodically sent to enable other node to connect to the DODAG. The DAO, destination advertisement object message packet, is mapped to OX02 and is used to transmit robust route information to record the node traverse along the upward path. So the children will transmit DAO, destination advertisement object, to their parents up to the and then it will continuously be transmitted up to the root node. And this will enable the parent record path, a means of reaching out to the children nodes. The DAO message are sent by each node other than the DODAG root to update the routing tables with prefixes of the children and to advertise their addresses and prefixes to their parents. A complete route between DODAG root and the node is set off after transmitting this destination advertisement object packet. The DAO packet is multicasted upward from the destination to source when there is a path update. As a response to a unicast DAO packet, a DAO ACK packet is transmitted by a DAO recipient, a parent or a DODAG root. DAO ACK holds information about RPL instance ID, DAO sequence, and status, which signify the completion. Now, status code are still not clearly stated, but code higher than 128 means a rejection. A node that is a node should elect a different parent. The story mode of operation is similar to how the conventional IP routers work, where every node keeps a next hop information toward the node in its subtree. The intermediate parent do not keep the DAO packets. Only add their own addresses to the reverse path stack in the received DAO packet, then forward it to the parent in the non-story mode of operation. The intermediate parent do not keep node do not store any information in the non-story mode of operation. Only the root node keep the complete topology information. Source routing technique is used beginning from the root and the root node only when a packet is routed downward. Non-story mode is more common in low powerless network in spite of the extra and inconsistencies packet overhead for IP version 6 header option resulting from source routing, which add the whole route information in the packet header. RPL provides both multi-point to point traffic, which pertains to data collection traffic forwarded in the upward route direction from multiple nodes to the DODAG root. The data collection traffic is referred to as inward unicast traffic. The multi-point to point traffic is the main traffic flow in most of low power loss network applications. RPL support multi-point to point traffic such that destination can be reached via the DODAG route. So the user of the network can be able to access data from the individual IoT devices with the use of this multi-point-to-point traffic, as we are seeing it in the IoT system model in Figure 1. Once a data route is constructed, it is used to build the upward route from the routers to the root. The deeper route from the node to the root are established through the preferred parent chain. RPL provides mechanism for point-to-point routing between any two nodes in the DODAG. In order to support point-to-point traffic in RPL network, a link border router must be able to transmit packet at which point it is source routed to the destination. Now, two cases arises. If the destination node is co-located within the sender node in the same transmission range, then the latter directly send the message to the destination without passing it through its parent. Else, the peer-to-peer mechanism will depend on whether the network is pre-configured as a storing or non-storing mode. Now, in the non-storing mode, routers do not store any information about downward route, no information about their descendants, and only the root possesses such information. In this case, any packet must be first sent through the DODAG upward route to the root, which will forward to its destination. In the storing mode, routers locally store the routing information about downward route. If the destination is a descendant of the router, then it forwards the message down to the closest router to the destination. If the destination is not a descendant, then the message is forwarded to the parent node, which will apply the same aforementioned rules to send the packet to its destination. As such, the packet will be forwarded to the uplink direction of the tree from the child to parent until reaching the router that is the first ancestor of both the source and the destination nodes. Move to security in RPL. Now, RPL has three basic security modes. We have the unsecured. In this mode, RPL control messages are sent without any additional security mechanisms. And we have the pre-installed, where in this mode, node joining RPL instance have pre-installed keys that enable them to process and generate secured RPL messages. And we have the authenticated. In authenticated mode, nodes have pre-installed keys as in the pre-installed mode in number 2, but these pre-installed keys may only be used to join RPL instance as a leaf. Now, RPL specifies a security mechanism to prevent its routing control messages and topology from external attackers, but it explicitly noted that this security mechanism is optional to implement. So basically, security feature in RPL is an optional measure. It's not something that is applied by default. It's not something that is mandated. RPL is weak for internal attackers, insider attackers that can carry out attacks such as version number attack, rank attack, disk transmission attack, high-powered DO transmission attack, Sybil, clone attack, Sinkhole, wormhole attack, redundant locally repair attack, and selective forwarding attack, and many other attacks. Now, these attacks spoil the routing topology and or incur large control overhead, which prevent reliable packet delivery and shortens battery lifetime. Attacks against RPL are covered in three groups: attack against resources, attacks on topology, and attacks on traffic. Now, attack on resources aims to deplete the resource of node in the network by causing unnecessary operations. And the attacks on topology affect the construction of RPL topology in a non-optimal way, or lead to the isolation of some node from topology. And attacks on traffic analyze network traffic in order to implement more complex attacks. Packet dropping attacks, now we move into what we call packet dropping attacks, one of the attacks in RPL. RPL security attacks, packet dropping attacks. Packet dropping attacks include Blackhole, Sinkhole, and Selective Forwarding Attack, also called Grey Hole Attack. Now, in Blackhole Attack, a malicious parent node drop all its children node packet. And a Sinkhole is a variation of the Blackhole Attack, where a malicious node facilitates the attack by forming a rank decrease attack. So it is basically two attacks in place, combination of a black hole and a rank decrease attack. That forms a sinkhole attack. Now, selective forwarding attack is another variation of the black hole attack, where a malicious node drop packets selectively. Okay, so let me go back to this sinkhole attack. Sinkhole attack, it will perform a rank decrease attack to make it more attractive, because the lower the rank of a node, the higher the chance of that node being selected as a parent by children node. So many nodes will select that as their parent since it has a lower rank. Lower rank means a closer proximity to the root node. So many nodes, it will become attractive for children node to select it as their parent. So when this node is being selected as parent of some nodes, it will drop their packet. So it uses rank decrease attack to facilitate a black hole attack. So basically a combination of rank decrease attack and a black hole attack form a sinkhole attack. Now we have selective forwarding attack is another variation of the black hole attack where malicious will drop packets selectively. Selective forwarding attack is further divided into selective forwarding attack 1, also called neglect and greed selective forwarding attack. Now the attacking node fully participate in the transmission and exchange of RPL control packets such as the DIS, the DO, the DAO, and the DAO acknowledgement, and they even acknowledge the reception of the packet to the sender, but they refuse to forward data packets. Now this is a SFA1 is shown in figure 6, where we have the malicious node, SFA2 attacker node, dropping all the packet of its children node. C, D, E, and F are children that belong to this malicious node, and when they forward their data packet for transmission to the root node, it will drop the packet. It will drop the data packet. An attacking node, and then we have SFA2. An attacking node drop a packet that originates from a particular node or group of nodes. That means it is selective in its form of attack. It selects a victim node, a one node, or multiple nodes to perform attack on them. Now, as you can see it in figure 7, where we have the malicious node, SFA, okay, this is a typo. It's supposed to be SFA2. SFA2. So it selects some children node. C, D are the victim node, that if they forward their data packet to this malicious node, it will drop their data packet. However, to E, the data packet coming from E and F, the malicious node will successfully transmit that data packet successfully. So the victim that it selects are C and D. Now we have moved to SFA3. Now in this category of SFA, the attacking node forward data packet to the wrong path, which leads to a creation of unfaithful routing information in the network. Multi-point to point, or many to one, point to multi-point, also one to many, and point to point, or one to one are the three communication paradigm enabled in RPL. And now SFA3 can exploit these features of the RPL to execute its attacks. Now SFA4. Now this is where a malicious node creates confused routing information between a sensor node by delaying the packet passing through it. So it doesn't transmit the packet on time. Then we move to another type of attack called wormhole attack. Now a wormhole is an out-of-band connection between two nodes using a wired or wireless link. This attack takes place by creating a tunnel between the two attackers and transmitting the traffic through it. Wormholes can be used to forward packets faster than via normal path. Then we move to another type of attack called clone ID, where a malicious node spoofs another node in the network. And this is done by exploiting the DIS packet. Then we have Sybil attack. And in Sybil attack, an attacker uses several logical entities on the same physical node. The Sybil attack can be used to take control over a large part of a network without deploying physical node. So it duplicates, it creates a peg nodes and distributes them on the network. This transmission mechanism can be exploited by antivirus to attack the network as well. Now, if the malicious node generates and multicast a large number of this message, piggyback with different fictitious identities. Now we move to another attack called Distributed attack. Now in the RPL, these messages are used by node to join the network. Node send this message to its neighbor node to get the routing information. RFC 6650 does not specify time interval for this transmission. This transmission interval may vary with different RPL implementations. A new node continuously transmits these messages. We know that this message is a packet used as a request to join a DODAG. Now a new node will continuously transmit these messages with a fixed interval of time until it receives a DO, that is DODAG information object, from any of its neighbor node. And a DO is a message granting the new node request to join the DODAG. Now in RPL, a node can send either a multicast or unicast this message. Based on the nature of the transmission, that is multicast or unicast, the receiver node responds in the following manner. Case 1, on receiving a multicast this, the receiver node reset its trickle timer and send a multicast DO message containing the latest routing information. And in case 2, on receiving a unicast this, the receiver node directly sends DO message to the sender node without resetting its trickle timer. With respect to the type of this transmission, multicast or unicast, this attack also falls into two categories: unicast this attack and multicast this attack. A multicast dispolluting attack, an attacker sends a multicast this message to its neighboring node frequently. And or receiving a multicast this message, neighbors within the range of attacker are forced to believe that there is some route inconsistency present in the network. Now, this in the neighbor reset their critical timer and transmit multicast DO message in the network. This frequent resetting of critical timers lead to an increase in the number of control messages being transmitted by the node. This increase of control packet overhead consequently forms a locally unstable network. The abrupt increase of control messages suppresses communication channel availability and increases overall power consumption of the network and further reduces the network lifetime. In unicast disk loading attack, an attacker sends either a unicast disk message to its node in the neighbor list, or it may send a unicast disk message to a target node. On receiving the unicast disk message, the non-attacker node replies the sender with a unicast DO message without resetting its critical timer. The unicast disk loading attack also affects the control packet overhead and overall power consumption of the network. The impact of unicast disk loading attack on the network is less as compared to multicast disk loading attack. However, both ways of sending this message add consequences on the network has no impact on delivery ratio, but this multicast attack shows most increase in end-to-end delay. This attack can generate more control overhead and hence energy exhausting. Now, another type of attack called rank attack. Now, by changing rank value, an attacker can attract a child node for selecting as parent or improve some other metric and can attract large traffic going towards the root. There are three types of rank attack. We have decreased rank attack, where a malicious node advertises lower rank with or without changes to the objective function to other node, resulting in many of them selecting the adversary as their preferred parent. Increased rank attack, where adversaries will be near the root node but advertises higher rank and worse routing metric. Increased rank attack introduces more energy consumption and higher overhead traffic. Then we have worst parent attack, which is hard to detect, as the adversary will simply advertise its actual rank but select the worst parent by itself. It can also use the decreased rank attack method to attract more nodes to select it as parent, while sending their packet to the worst path, resulting in increased less able routing loops. The worst parent attack results in network sub-optimization and increased end-to-end delay as expected. Excuse me. Then we have version number attack, where the root, in a normal scenario, only a root node is supposed to change the version number of the DODAG. But the current RPL standard does not have any mechanism to assure the integrity of the communicated version number. Now, if a malicious node sends a DO message with higher version number, it will pause global repair procedure to start and create topology inconsistency around root, especially if the malicious node was far from the root node. Now, the main goal of version number attack is to exhaust node resources and slow down packet delivery to a crawl. A local another type of attack called local repair attack. And a local repair attacker without any problem with link quality periodically send local repair message. Now, and this will cause a local repair around the node, which hears the local repair message and result in the node constructing the same topology again. Local repair attack create more impact on delivery ratio than any other kind of attack and generate more control packet and increases end-to-end delay. The main goal of this attack is to create much more control overhead and exhaust node resources. Now, RPL, another attack called neighbor attack. Now, in this attack, malicious node broadcasts DO message that is received without adding any information of itself. The node who received this type of message may think that the new node sent this DO message. The victim node tries to select the node which is not a range as the parent node and change the route to the out of range neighbors. Another alteration to this attack is known as route information replay attacks, where an adversary stores control message from other node, then send them later to its neighbors, forcing them to update their routing tables with outdated data. Then we have a routing table overload attack, where since each node maintains its own routing table, an adversary can send many bogus routes via DAO message to the compromised node till it is saturated. This will prevent the compromised node from accepting legitimate DAO message and build correct route. Routing table overload attack is a resource exhaustion attack. Then we have another form of routing table attack called routing table falsification attacks, where a malicious node will advertise fake route to other nodes, whether this node exists but not in the subdodac of the adversary or entirely forged. This causes packet losses in case of forged route or longer end-to-end delays. And this attack causes resource exhaustion for the compromised node due to increased control overhead and repetitive repair attempts. Then we have a replay attack, where the idea behind this attack is to record legitimate control message, DO, DIS, and DAO, and forward them later in the network. Such attack will result in outdated or false routing entries, degrade routing service, lower packet delivery rate, and in some cases, detachment of the victim subdomain. So thank you very much for watching and listening to this presentation. This bring an end to this presentation, and you can follow this tutorial series that I am creating, and also more update on my Researchgate page, where I am conducting a research on this RPL security of this RPL routing protocol in the Internet of Things. So thank you very much for listening and watching my presentation.